Hello everyone, we are going to study in this video about stereochemistry from chapter haloalkanes and haloarenes. First, let us understand the meaning of the word stereo. The word stereo talks about space and stereochemistry talks about the spatial arrangement of atoms. How are the atoms arranged in a molecule? Let us take the first definition over here, configuration. So configuration is the first definition which we have to study here. It means the three-dimensional arrangement of atoms. It means three-dimensional arrangement of atoms. And how are we going to represent the molecule of a carbon compound is this way. First we will draw two solid lines which indicate that the bond is in the paper, a wedge line which means that the bond is towards the observer, and the dashed line which means that the bond is away from the observer. Now this particular carbon atom is attached by 4 bonds. We may attach any groups of our choice like this. So this is the meaning of the word configuration, the three-dimensional arrangement of atoms. How are the atoms arranged? Are they on the paper? Are they away from you, like hydrogen is away from us and CH3 it is towards us? Now when we see this particular figure, we have this carbon atom which is denoted by an asterisk. It is called chiral carbon atom. Now the meaning of the word chiral carbon atom is the carbon atom which is attached to 4 substituents. 4 different substituents. The substituents have to be different, they cannot be same, and such a carbon which is attached to 4 different substituents will be called as chiral carbon atom, and this condition or the property the molecule is having is called as chirality. Now I am going to draw a chiral molecule once again and show you its mirror image. Now this is my first compound which is optically active. Let us denote this compound as A, and we can draw its mirror image. This is the mirror, and exactly the opposite we are going to draw. The bonds which are projecting right side, we will project them towards the left side, and this becomes CH3, this becomes OH. Then we have your hydrogen atom which is this side, and the dashed lines which will be going away from the observer. So this is C2H5 and this is your structure number B. So here we have to understand that these are two different compounds. Spatially they are different. So they are called as stereoisomers. So these are the stereoisomers which are having some relationship as mirror images. So these stereoisomers are going to be non-superimposable mirror images. And hence such stereoisomers which are having this kind of relationship are called as enantiomers. So what are enantiomers? We have understood that the compounds which are non-superimposable mirror images. For an example, we can take my hand, for example, my right hand and the left hand. They are mirror images. If I try to superimpose one hand over the other, then they do not coincide, they do not superimpose. So these two, right hand and the left hand, are going to be called as enantiomers. The next definition is polarimeter. Polarimeter is a device which measures the optical rotation. What is an optical rotation? Let us understand it with the help of a figure. So to understand what is a polarimeter and how it works, we will have a look at this diagram. So this is your ordinary light or white light which has got many planes of electromagnetic radiations. So infinite number of planes are there in a white light. This light has to be passed through a specially designed prism called as Nichols prism, which is made up of crystalline calcium carbonate. This prism is going to absorb all the planes except for one plane. This light which is emerging out of Nichols prism is called as plane polarized light. So the speciality of this light is that it has got only one plane. This is the plane which we are going to investigate by passing this light through a compound which is under investigation. What happens to this light when it passes through this compound, we will see. Now here we can see that originally the plane was in this way. It was originally oriented this way, and after the compound, it passes through the compound, the plane has got deviated at around plus 10 degrees. So we'll say that, and this is an assumption, plus 10 degrees or whatever angle it is deviating to. So this kind of compound which can rotate the plane polarized light by some angle is going to be called as optically active compound. So this is your optically active compound. Let us say I had taken the compound A in this test tube. So A is going to have an optical rotation of plus 10 degrees, and in the similar manner, if I replace this compound by its mirror image, that is A dash, what we will find is that it is going to rotate the plane polarized light by minus 10 degrees. So this is what we find, that the two enantiomers are going to have the same magnitude of optical rotation but opposite signs. One is going to be rotating the light in the clockwise direction and the other is going to rotate the light in the anti-clockwise direction. So now we will understand the meaning of the words dextrorotatory compound, levorotatory compound and racemic mixture. Now in the previous figure we discussed what is a dextrorotatory compound. That is the compound which rotates the light in clockwise direction. Like the compound A was having an optical rotation of plus 10 degrees, so it was said to be a dextrorotatory compound. For example, we will say that a compound like butane 2-ol is going to be dextrorotatory, so we'll write it as, symbolize it as D-butane 2-ol. So how to write the symbol of such compound is writing the letter D and the compound's name. Instead of writing D, we may also substitute it by writing plus sign. So these are the two different ways in which we can denote a dextrorotatory compound. Same way, it's the other half of the compound, that is the mirror image of that compound, A dash, was rotating the light by minus 10 degrees. So such compounds which rotate the plane polarized light in anti-clockwise direction are going to be known as levorotatory compound, indicated by the symbol L or the sign minus. For example, if levorotatory butane 2-ol has to be written, it will be written like this. Similarly, I can write it as minus butane 2-ol. The next is racemic mixture. Now, if two enantiomers like butane 2-ol D and butane 2-ol L are mixed in equal amounts, then that mixture is called as racemic mixture. It's a common sense that if I mixed enantiomer A and the enantiomer A dash in equal amounts, that is 1:1 ratio, the optical rotation of the A will be plus 10 degrees, optical rotation of A dash is minus 10 degrees, so the overall optical activity is going to be 0 degrees. So racemic mixture is going to be optically inactive. To represent racemic mixture, the way we are using the symbol D, L, plus, minus, for racemic mixture also we are going to use the symbol collectively D, L or plus minus. So if I want to represent butane 2-ol, I will be writing DL butane 2-ol, which means it is a racemic mixture. Okay, so there's a new word, racemization, the process of making a racemic mixture. How do we do that? Is by mixing equal amounts of both the enantiomers. Now let us identify out of these compounds which are optically active and which contain the chiral carbon atoms. The first structure we will see. In the first structure there are two carbon atoms, 1 and 2. This carbon atom is attached to 3 carbons, so this is not chiral. But this carbon is attached to two same hydrogen atoms, one OH, one CH3. Since this is also not attached to a chiral carbon atom, to 4 different substituents, this is not chiral. Since it is not chiral, it is not optically active also. Here there is CH3 which is not chiral carbon atom, here CH2 not chiral. This is C with one H, one CH2 CH3, one CH, CH3 CH2, CH3 and OH. So this one is a chiral carbon atom. Since this is chiral carbon atom, this is going to be optically active. Why? Because this is attached to 4 different substituents. Look at this. Now here nobody is chiral carbon because they are all attached to 2 hydrogen atoms, as we can see and make out. Over here this is not But this, yes, this is chiral because it's attached to OH, NH2, CH3 and a different cyclohexyl group is chiral. Coming to the structure number 4, just number them once, 3, 4, 5. So in the structure number 4 also you can see that it's evident this is CH2 not chiral, CH2, CH2, CH2. So all these are not chiral, but this carbon atom, yes, is going to be chiral because it is attached to totally different groups on all the 4 sides, chiral and optically active. Let us look at this one now. In this compound you can see that there are going to be non-chiral, non-chiral. Yes, this is chiral because it is attached to CH3, OH, H and a different group. This carbon is attached to H, OH, CH3 and a different group. Both are chiral. Looks like it should be optically active. Looks like. So the first condition it has fulfilled, that is it has having chirality. And number 2, if we try to talk about, if we see its optical rotation, actually speaking, it is having 0 optical rotation. So what is the reason for 0 degrees optical rotation though it is chiral? So if you look at the structure very carefully, you will see that there is a mirror plane going from here, due to which the molecule gets divided into 2 equal halves. So this compound is actually having an element of symmetry or a plane of symmetry. Since it is having a plane of symmetry, it is, like similar parts are there on both the sides. If one part of the molecule rotates in anti-clockwise direction, the other half rotates in clockwise direction. So due to this, the optical activity gets cancelled out internally. So such compounds which have a plane of symmetry will be called as mesocompounds. So that's all from this video. We'll continue in the next class. Thank you, keep watching, bye bye, and do subscribe.